With every mechanics question, there's going to be a theme, a general topic that you can hopefully identify fairly quickly. And once you know the overall topic, you should have a plan of action in place that is going to be relevant to pretty much any question you get on that topic. So for instance, this question here, talking about a car moving along the road for a certain length of time with a certain speed, accelerating at a fixed rate, we know that we're dealing with a constant acceleration question. And the first things that should come to mind are there are Suvat equations in the formula book that are directly relevant. We've got to pay attention to the direction. So think about whether we're going forwards or backwards, if things are speeding up or slowing down, whether acceleration is going to be a positive or a negative. Take care to use the correct value for G. It'll be given a default value at the very beginning of the paper, and if they want you to use something different, they'll say it within the question. Other things you can do, it's worth thinking about the different phases of motion. So if things are happening with constant acceleration, then Suvat equations apply. But if the constant acceleration at a certain point suddenly switches to a different constant acceleration, you can still use Suvat for that second part of the question, but you have to do it separately. So it might be that you find the final speed from phase 1 and use that as the initial speed in phase 2. The other thing you can do, which is sometimes, as in this question, specifically requested, and sometimes you might choose to do it because it's going to help you to visualize the situation, is sketch yourself a velocity time graph. Remember, the gradient of your graph represents the acceleration because it's the rate of change of velocity, and the area will give you displacement, including if it's below the axis, giving you a negative displacement, because the integral of the velocity graph will give you the displacement. And it's worth remembering, if one particle catches up with another particle, it means it's in the same position at the same moment in time. If you're dealing with a question involving two separate particles, whether it's a person in a lift or a truck pulling a trailer or two particles connected by a string over a pulley, then the best thing to do is to make sure you've got a really clear force diagram. Think in particular about the forces acting on each individual particle within the scenario. So if you've got a person inside a lift, consider separately the forces on the person, the lift pushing up from below, the reaction force from the floor, and their own weight pulling down. And then consider the forces on the lift, the cable pulling it upwards and its own weight and the reaction force from the man pushing down. With this question, for instance, we've got two particles, one of them on a slope, so the forces acting on that one will include potentially friction from the slope, unless it's modelled as smooth, tension from the string, the weight pulling directly down, and the reaction force pulling perpendicular to the slope upwards. Things you can always do with questions like this, consider the forces in the direction that the thing is moving or accelerating and use F equals ma. Or if it's not accelerating in a particular direction, like the object on the slope is accelerating up the slope, but it's not accelerating perpendicular to the slope, you can use the fact that the out from the slope forces match and balance the in slope forces. In other words, there's a net zero force perpendicular to the slope. Often you'll have a situation where there'll be two unknowns, like the acceleration that the particles experience and the tension in the string between them, and you can solve simultaneously because you'll have two different particles to investigate. In a question like this, where you're given the acceleration in terms of t, whether or not there are vectors involved, you have to remember that this is no longer a constant acceleration situation. This is variable acceleration, which means you've got to take into account how calculus can help us with the question. Velocity is defined as the rate of change of displacement, and acceleration is the rate at which your velocity changes. That's why the units for velocity are meters per second, and the units for acceleration are meters per second per second. It's a rate at which another rate changes. So you can differentiate position to get velocity, and you can differentiate velocity to get acceleration, or you can work backwards by integrating. But when you integrate, you've got to remember to take into account the constant of integration. That's the reason in a question like this, they might tell you the initial velocity so that you can calculate that unknown constant. In a projectile motions question, even if they don't give you a diagram, you can sketch yourself a diagram if it's going to be helpful. You want to think specifically about how the vertical and the horizontal motion behave because they're independent. You can do this as a vectors question if you like. A lot of people find it easier to think separately about what's happening vertically and use Suvat, and what's happening horizontally and just use displacement equals speed times time, or something like that. It's constant speed in the horizontal direction, so it will always be the same. And in the vertical direction, you'll have a variable speed, but a constant acceleration. So you can make use of your Suvat equations for that one. When you've got moments involved, typically it'll be pretty obvious, because instead of dealing with a particle with forces acting on it, you'll be dealing with a larger object, typically a one-dimensional object, like something that's being modeled as a rod. Maybe it's a plank over a river, maybe it's a ladder leaning up against a wall, but we're taking into account not just the forces, but also where on the object the forces act. So in this particular question, we've got something leaning up against a smooth peg. There'll be a force from the peg holding the thing up. There'll be the reaction force from the ground holding it up. There'll be a frictional force if there's a rough surface, and of course the weight of the object itself. The most important thing to take into account with a question like this is your force diagram. Make it big, make it clear, include all the forces in the appropriate directions and the distances between where they act. You want to take into account friction, normal reaction, any angles you're given. If, like in this question, they give you a clue about the angle, sine alpha equals 4/5, or if they tell you tan alpha equals 4/3 or something, you can use that to find nice fractional values for sine theta and cos theta without necessarily ever working out the actual angle itself in degrees. Then the main things you're going to do are take moments, pick a point where lots of different forces act, and then those forces won't appear in your equation because they're a zero distance away from the point. And then you can resolve forces in two different directions. So for a question like this, where most of the forces will be vertical or horizontal, resolve vertically, resolve horizontally. When you take moments, sometimes it's more efficient to use the perpendicular force multiplied by the distance, and sometimes it's easier to use the perpendicular distance to the line of the force and then just multiply by the force. They both come out exactly the same. And the final thing to remember is you can always construct another equation connecting the forces together, because friction at its maximum is equal to mu times r. So when you're dealing with a mechanics question, figure out which general topic you're working with and then apply these basic principles. The next thing I'm going to do is work through a few of those exam questions in a bit more detail so you can see how we would do this in practice. In this question, we have a car moving along a straight horizontal road, starts from rest, moves with a constant acceleration for a fixed amount of time, and they give us the speed that it gets to at the end. This speed is then maintained. It means once you've reached that speed, you'll continue at that same speed. So the motion changes at that point from a constant positive acceleration to a zero acceleration. The speed is constant from that point on. After the car has been moving for 15 seconds, a motorbike begins. So up until this point, the motorbike hasn't been moving and it's not in the equation at all. But now the motorbike appears, it's accelerating probably more quickly with the car because eventually it catches up with the car. And it says it catches up when the car's been moving for t seconds. That's the total amount of time the car's been going for. And even if they hadn't said draw a speed time graph of the car and the motorbike, that would have been a sensible starting point. But it is possible to describe this using Suvat equations as well. So for instance, the first phase of motion, the car is accelerating. We don't know how far it's gone, but we do know that it starts from rest. We're told that it reaches a speed of 15. We're not told the acceleration, but we are told that it takes 30 seconds to get there. The next phase of motion is where the car reaches its speed of 15 and that speed is maintained. So all we need here is S, U and T. I'm using 15 for the velocity, but the time that goes by during this second phase of motion is not the same as capital T, because capital T is the total time the car has been driving. The time we have is T minus 30 because it's the additional time that the car has been driving since it changed from accelerating to cruising speed. And the other phase to consider, which is kind of independent of these to some extent, is the bike itself, which is accelerating throughout its motion. And we can look at, we don't know how far it's gone, but we do know it starts from rest. We don't know how fast it's going at the end of motion, but we do know that it's accelerating at a rate of 1.5. The other thing we have is the time that it's been going for. And if the car has been moving for t seconds, and the motorbike didn't start until after the car had been moving for 15 seconds, it means the total time the motorbike has been accelerating for is t minus 15. Our graph should end up looking something like this. The car is the one that accelerates until the point when it turns into a level horizontal line, and the motorbike is the other one. We don't have a particular point to mark on here, so I've given it a value t, and you can see that we've put that further along than perhaps you might have guessed. It's a very tempting thing to assume that the bike catches up with the car as soon as the two lines cross. But remember, this is a velocity time graph. So what you're looking at the point where the two lines cross is the moment when the velocity of the car matches the velocity of the motorbike. What we want is when the distance covered by each of them is the same. So we're actually looking for when the area under the graph is the same. And one of the nicest ways to do this is probably to calculate the area under the graph directly in terms of t for both of these. And the clearer your graph, the easier that's going to be. But you can also do it if you prefer in a more algebraic way using suvat. So we want to work out when they've covered the same distance. I'm going to break it down into steps for myself. I want to work out how far the car goes in the first 30 seconds. That's equivalent to the area under the triangle from the origin up to the point 30, 15. And then I want the distance covered by the car in the following t minus 30 seconds, the little rectangle that will be left behind. And then the distance covered by the bike during the time when it is moving. Finally, I'll put the two distances equal to each other and find out the value of t that makes those the same. At the very end, the last part of the question, find the speed of the motorbike at the instant when it catches up the car. I need to work out how fast the motorbike is going at the moment that we've already determined. So I'll go back to the motorbike phase 3 and substitute my number in. Let's give this a try. The distance covered by the car in the first 30 seconds you can either do using the area of the triangle or with suvat equations. The distance covered in the next t minus 30 seconds, we can use that simplified equation for the constant speed. Speed equals distance over time, so displacement equals speed times time, 15 times t minus 30. The bike during the t minus 15 seconds, again suvat equations gives us an expression for that. We put them equal to each other, we get an equation. If you look carefully, you'll notice this is a quadratic equation, so we're likely to get two different values for t. And that's what happens. When we expand things out and simplify, it is possible to write this more nicely. If at the beginning you divided everything by 0.75, the numbers would come out more pleasantly. You might even see how to factorize it for yourself. But it's not necessarily worth spending time doing that if you've got a calculator that can solve it for you. I get two values and both appear to be sensible until you think about what we assumed at the beginning. Look at the graph. We haven't specified exactly where t goes, but we have assumed it happens after the car reaches its cruising speed, which makes sense. If you look at the graph and assume that t is smaller than 30, then it doesn't look like the motorbike will have gone as far as the car. And certainly if my two choices are t equals 15 or t equals 35, that doesn't make any sense, because after 15 seconds, the motorbike hasn't moved at all. The reason the equation is giving us a 15 is that we've made the assumption initially that we've traveled further than, for longer than 30 seconds. We've assumed we want the complete triangle plus a bit of the rectangle that's coming later. So that assumption has meant that only one of our answers is valid, and that answer is one that makes perfect sense. So about 5 seconds after the car reaches cruising speed, the motorbike has covered enough distance to catch up. And the last bit, substitute it back in to find the speed of the bike, another suvat equation, but now we have not just the initial speed and the acceleration, but we know the time taken because it's capital T minus 15. The bike at that moment is going twice as fast as the car. Remember, the only reason it had to be going so much faster is that it started later and it's been accelerating all this time. Arguably, it could have stopped accelerating at any point when it was going faster than the car and maintained its speed. It would still have overtaken eventually, but this way it overtakes faster. The first thing I've done with this question is draw the diagram a lot bigger. It's really helpful to scribble on the diagram in the exam paper, but it's usually a good idea to draw your own, make it nice and big and clear. Perhaps your first draft is scribbling on the exam paper and the second draft is marking on exactly what you want for your own force diagram once you've taken into account everything that's given in the question. So for starters, we've got the weight pulling down on this particle and we've got tension pulling back up. Then we've got weight on this particle, again pulling directly down, which means slightly down the slope and slightly into the slope. And we have tension pulling up. There's a reaction force perpendicular to the slope on this particle, and if it had been a rough slope, we'd have needed to include friction as well. Since it doesn't involve friction, this particular one, the reaction force becomes irrelevant, but it's good practice to include all the forces anyway. The other thing I like to include on my diagrams is an indicator for which way the objects might be accelerating. This helps me to get a direction for the equations I'm going to make. One other thing that can be helpful, if they've given you information about the angle, here they've told me sine theta is 2/7, it's possible that I'm going to need cos theta as well. Not necessarily the case, but it's often a time saver if they give you sine theta or they give you tan theta to work out sine and cos, so that when they appear within equations later on, you'll already have them as nice values. You can do this with the calculator using inverse sine followed by cos of the answer, or you can square 2/7, subtract from 1 and square root using the Pythagorean identity to jump straight from the sine to the cos. There's nothing wrong, of course, with also drawing yourself out a little right angle triangle. The opposite side is 2, the hypotenuse is 7, Pythagoras gives you the adjacent side 3√5, and then you can do adjacent divided by hypotenuse to get cos. This is what I'm going to do for the first part. I want to know what the tension is. Well, I'm going to do what I always do with connected particles questions. I'm going to look separately at each particle, set up an equation of motion for each one involving F equals ma, and then I solve simultaneously. I'll find the tension and I'll also find the acceleration. And based on what the next bit of the question is asking, it's going to be helpful to know what the acceleration is. For the next part, it talks about after particle B hits the ground, particle A continues to slide up the slope briefly, and then it comes to instantaneous rest at a certain point. In other words, even though it suddenly has no tension pulling on it, it's still going to be moving up the slope because it had some upslope velocity at the instant when the string became slack. In order for it to come to rest, it needs to reduce its speed. And it will be reducing its speed because the overall force acting on it is now in the downslope direction. Because the tension's gone, the only force acting with the slope is going to be a component of the weight force. So we'll have a new acceleration for that object, and that acceleration is in the downslope direction, in the opposite direction to which way the thing is moving. So we can use Suvat equations, but we'll have that different acceleration to take into account. We'll also need Suvat for while it's accelerating up the slope, so we can work out how fast it's going at the moment when the string snaps. And at the end, we'll have to take care with the distances we've calculated to make sure we give an answer which is the one expected. The distance from the initial starting point to that moment when it comes instantaneously to rest. That's a combination of two different distances. So let's dive in. Firstly, for particle B, F equals ma means the overall net force or resultant force in a particular direction. I'm going to go downwards because that's the direction that this particle is accelerating. 3g is pulling down, t is pulling up, and the ma side of the equation, the mass is 3, the acceleration is a. We can't solve for t or for a with just one equation, but if we do the same thing for particle A, we'll be able to solve simultaneously. For particle A, t is pulling up, 3g sine theta is pulling down. If it helps, you can draw on the additional information about the angle at particle A. So if you were to draw a dotted line perpendicular to the slope, you could convince yourself that the angle between the weight force and that perpendicular to the slope is the same as theta, and that means we need 3g sine theta to work out how much force is pulling down the slope. This can be simplified because remember in the question they told us what sine theta was. So replacing sine theta with 2/7 gives us this slightly nicer equation, and then I'm going to solve simultaneously. With this particular case, if the question has asked you for t, maybe it makes the most sense to try to solve for t first of all. We could use the fact that both equations have 3a on the right hand side, but most commonly you're going to need t and a, and in fact in this question you need both anyway. So I'm going to do what I normally do, which is add the left hand sides and add the right hand sides, and that way the t will cancel out because it's positive in one equation, negative in the other one. As soon as I do that, I get an equation that involves only a, or at least only a and g, but I'm happy to keep g kicking around as a constant in there for the time being. It'll make my calculations a bit nicer. Once I've got A, I can go back to any of the equations I like and substitute that in and get a value for t. If you want to be on the safe side, test in the other equation and see if those values still work. The next thing to do is consider the motion of the two particles. First of all, while B is falling, it falls 0.8 meters. It starts from rest. We don't know how fast it's going at the end. That's actually what we want to find out. We do know the acceleration. That was the 5g/14 that we just calculated. And we don't know or care about the time it takes. With that information, those three known values, we can find the unknown value. The most sensible equation to try here is the one that links the three values we know with the one value we don't know and that we want. So I can calculate v squared more easily than v. And v is the square root of 4g/7, which I'm going to leave in that form because it might well be that I'm using a similar equation in the next bit anyway. So a new force diagram is probably a good idea at this point. You could just scribble over your old one, but sometimes it's helpful to draw a little quick force diagram to remind you of what the new situation is. Now this object is no longer accelerating up the slope. In fact, it's going to be accelerating back down the slope. And we can see that the only force that matters is the downslope component of the weight. That 3g sine theta that was pulling down in the first place is still pulling down, but tension has disappeared. So you can think of this as the same equation we had for particle A previously, but with t taken away. We've removed t, we've set t equal to 0 effectively, and we're recalculating the acceleration. And what we get is 3g sine alpha in the downslope direction is equal to the mass of 3 times the acceleration. So the acceleration is g times sine theta, but sine theta is 2/7. So now we've got the new acceleration. It's in the downslope direction and it has a magnitude of 2/7 of g. That allows me to do phase 2. While A is decelerating in the upslope direction, we don't know the distance, we do know the speed. The initial speed for this phase is equal to the final speed for the previous phase. We do know that it comes instantaneously to rest. In other words, what we're interested in is how long it takes, or rather how far it goes while it's reaching the point where it stops. The acceleration is in the downslope direction. So if I'm using positive or up the slope as positive in this case, I'm going to need the acceleration to be a negative. And again, I don't know or care about the time. Since I know u, v, and a, and I want s, I'm going to use the same equation I used before. V squared equals u squared plus 2as. And that means I can use my u squared as 4g/7, which makes this much nicer, more precise than it otherwise would have been with lots of rounded values. The distance is exactly 1 meter. We just have to go back, reread the question, and convince ourselves that what we're calculating is what we're supposed to be calculating. It wants the total distance it covers, and because the distance includes the 0.8 meters it goes while it's moving up the slope, we add those two together. The final answer is 1.8 meters. This question involves variable acceleration. We can tell because it gives us the acceleration as a vector, and clearly as time changes, the acceleration changes. So even though we can't use Suva equations, we can use calculus. The first thing I'm going to do is integrate the acceleration to find the velocity. They're asking me about the velocity at a particular moment in time. If I use integration, I can get a general expression for the velocity at any moment in time, and then I can sub in the right value for t. But before I do that, it tells me at the instant when t equals 0, the velocity of p is 36 I meters per second. I've got to take that into account. You can see I've got a c1 and a c2 constants of integration in my vector. So if I can use those initial conditions, I should be able to find the values of c1 and c2. Most of the time, if your expressions like these are just polynomials, it might feel like overkill to set v equal to 36, 0 and substitute in 0 instead of just saying, well, surely my first constant is 36 and my second one is 0. But if there are other functions involved, it's not always going to be as simple as this. So it's a good habit to get into to do this properly, to substitute in 0 to see what you get. But in this case, the first constant is 36, the second constant is 0. Once you've got an expression for v, I can substitute in t equals 4 and I get a particular velocity. I'm keeping it in vector form because if I work out the size of this vector, I'm no longer giving the velocity, I'd just be talking about the speed. The velocity incorporates within itself information about the size and the direction that it's moving. Find the value of t at the instant when it's moving in a direction perpendicular to I. So this question is about the direction of motion which is to do with the direction of the velocity vector. So perpendicular to I, the vector I is the vector 1, 0. Perpendicular to that will be the vector j, 0, 1, or any scaled up version of that. So I'm going to put lambda times 0, 1. That way I'm describing all possible vectors that are perpendicular to the vector I. If I set the velocity vector equal to that, it turns out all I care about is the top row, because the bottom number is allowed to be anything at all. The top number, the I component, has to be equal to 0. If I set it equal to 0, I get two possible values of t, but of course t is a positive value because at the very beginning of the question it says at time t seconds where t is greater than or equal to 0. In other words, the motion we know about is only for positive or non-negative values of t. So the time is 4.5. The next part of this question, part 2, is a completely independent question. It's just the same topic. That's what we'll look at next. We can differentiate the position that we're given to find the velocity. If the position t squared minus t, 3t, then we get velocity 2t minus 1, 3. And once we've got the velocity, we can find the moment when the speed is 5 by using the fact that speed is the magnitude of velocity. To get the magnitude of a vector, you square the two components, add the results together and square root. I've skipped the square rooting step because it's easier to say the square of the magnitude is equal to the square of 5, and that gives me a slightly nicer equation to solve. So I can plug that in, I get two different values for t, only one of them is valid, so t equals 2.5. This question involves projectiles, so my go-to technique is to split the motion separately to look at vertical motion using Suvat equations and then horizontal motion later using S equals ut. So the vertical motion first. If the object is projected from horizontal ground and then it hits the ground again, the vertical displacement is 0. The overall change in height from the beginning to the end of motion is 0. It's neither higher nor lower at the end than it was at the beginning. The initial speed is u times sine theta because we're looking at the initial vertical speed, the upward speed, and because acceleration acts downwards, I'm given that a negative. S equals ut plus half at squared will allow me to calculate the time, and I know that time is the most useful thing to find because that's the thing that connects vertical and horizontal motion together. Now obviously there are two moments in time when the object will have a 0 vertical displacement, but one of those moments is right at the very beginning before it flies through the air. The other moment is the time we're interested in. That's the moment when it lands. So when I look at horizontal motion, I don't know the distance. That's what I'm being asked to find. OA is the distance between where it's projected and where it lands. U, the initial horizontal speed, is u cos theta, and t is going to be the second of those two t values. Just a minor point if you're a little concerned about having u equals u cos theta or u equals u sine theta. In this particular context, we can get away with it as long as we're careful and we don't confuse ourselves, because the u that I have before the equal sign is implicitly the initial velocity for vertical motion or the velocity for horizontal motion. And as long as I use things appropriately, I can get away with this sort of duplicate naming. It's kind of within the scope of what I'm talking about because the Suvat equations have their particular letters that we use. Normally exam questions will avoid this issue entirely by having something like a capital U for the initial speed. Anyway, horizontal motion using the value of t that we got from vertical allows me to use S equals ut, distance equals speed times time, and when I substitute numbers in and rearrange a little bit, I get the expression they're looking for. The only sneaky bit here is that you have to remember that 2 sine theta cos theta can be simplified to sine 2 theta. But if you forget, you can compare yours to theirs and say what's different. Well, is it possible that sine 2 theta can be constructed from my 2 sine theta cos theta? And as long as you can convince yourself that that's a valid step, you can write it in and you're done. For the next bit, they start giving us additional bits of information. If the speed is actually not just u, but 25, then can we find the largest possible angle for which the range is 40 meters? So the first thing to do is to solve and find what possible angle or angles would give that range. I can set the range to be 40 in the expression that we calculated in part A. So if the range is 40, I know that u squared sine 2 theta over g is 40. But I'm also given the speed, so instead of u, I've got 25. When I rearrange, I get two values for 2 theta, and I've got two values for a very good reason. They've asked me for the largest possible angle. And if you think about the nature of projectile motion, if you go at 45 degrees, you get the maximum possible range. If you go slightly above or slightly below, the range will be a bit lower. So for instance, 30 degrees, you get the same range as at 60 degrees. It's just that the ball is in the air for longer when it's fired at 60 degrees, but it's moving sideways more slowly, and the two things cancel out and combine to give you exactly the same range. What we're looking at here is a way of calculating the two angles that both give the same range. When I divide by 2, I get the two different values of theta that correspond to that range. You'll notice they add together to make 90. That comes from the fact that the 2 theta values were constructed using the symmetry of a sine graph. If 38.8 is a valid solution, then 180 minus 38.8 will give another valid solution. The trick here is to find all possible solutions within the modified range. They even mention in the question the angle of projection is between 0 and 90, which means 2 theta has to be between 0 and 180, and I've got to look at all the possible angles there, and that's how I identify the one I want. The next bit of the question says that theta is 30 degrees, so now I've got not just u but also theta, and they want to know how long it's more than 3 meters above the ground for. So I'm going to look at the vertical motion and say, when is it exactly 3 meters above the ground? If I can find the two moments in time when its height is 3 meters, I can just figure out how long it is between those two moments. Luckily for me, after I put in my suva, I end up with a quadratic. So the initial speed is not just u sine theta, but 25 sine 30. Acceleration I already know is going to be due to gravity downwards, and I'm looking for the two moments when the vertical displacement is 3 meters. When I rearrange and solve, let the calculator do the work, there are two moments in time. Presumably 0.268 seconds is on the way up when it first reaches a height of 3 meters, and then the 2.28 must be shortly afterwards when it's on the way down and it's once again at a height of 3. Therefore it's going to be more than 3 meters above the ground between those two moments. So I just subtract the two, and I'm going to round to two significant figures because I used a value for g which was accurate to two significant figures. I'm assuming g is 9.8 when I put these in my calculator. This one is a moments question. Often with questions like this, there's going to be a whole paragraph full of information that you need to skim through initially to get a feel for what's happening, and then read more carefully, go through with a fine-tooth comb and pull out every piece of information you can. Try to represent it on a nice big diagram. So for instance, the ladder has a mass m and length 6a. If you skim down a bit further, you'll see we're modeling it as a uniform rod. So now we know not just what the weight is going to be, mg, but also where it's going to act, 3a away from each end. So we get those two bits of information in first. The next thing we can do is, well, I don't know the distance to the point C, but they give us a clue about it, which is also already on the diagram. The point C is at a height 4a above the ground. I'm going to leave that as x for now, but I'm going to try to calculate that before I do too much more work. It should be possible, I think, because we know the angle already. We know that sine alpha is 4/5. It says it's rough horizontal ground, so I'm going to include a frictional force. If it's on the ground at all, there's going to be a normal reaction force there. And the fact that it's resting on a peg means the peg is going to be exerting some kind of force perpendicular to the rail. The reason I know it's perpendicular is because it tells me it's a smooth peg that it's resting on. A fixed, smooth, horizontal rail. Smooth means there's going to be no force parallel to the rod because there's nothing stopping it sliding across the rail, but there's always going to be a perpendicular force, the normal reaction force. The other thing I like to do, if they give me information like here's what sine alpha is equal to, I'll use that to work out what cos alpha is, so that whichever one I need later on in the question, I can read it off directly as a nice fraction. And then I'm going to look at the triangle that I think should tell me the distance x. The vertical height from C to D is 4a, and I'm interested in the hypotenuse, the distance from A to C. And I already know sine of alpha. So if sine alpha is opposite over hypotenuse, but sine alpha is also 4/5, then it doesn't take much rearranging to discover that x is equal to 2a, which kind of makes sense. That means the opposite side is 4a and the hypotenuse is 5a, and 4a over 5a is 4/5. So they've designed the numbers to work quite nicely, and it means now I can replace x with 2a. Next, we do the standard things we always do. In fact, you could almost get away with finding most, if not all, the marks in a moments question just by taking moments and resolving forces and then doing some sensible things afterwards. I don't recommend it. It's a good idea to read the question, but if you're not sure where to begin, take moments, resolve forces, see if you've got friction involved. They're the standard things. I like to take moments about the bottom, that point A, where you've got two forces already. We still don't know what R and friction will be, but we don't need to in order to take moments about that point. We'll get an equation that doesn't involve them at all because they're a zero distance away. So the distance to the point C is 5a, and that one is already a perpendicular force. The rule with moments is perpendicular force times distance, or if you prefer, perpendicular distance times force. Either way, this force is perpendicular to the line AC, so all I need is that distance 5a and the force S. The weight is a little more complicated. We have to work out either how far away the weight force is perpendicularly from A. In other words, imagine dropping a perpendicular down from mg and then working out how far away that line is from A. That's going to be 3a cos alpha. Or you can work out how much of the weight force is pulling into or perpendicular to the rod, and that's going to be mg cos alpha. Either way, there's a cos alpha in there. You're going to need to either multiply mg cos alpha by 3a or multiply 3a cos alpha by mg. So you get the same thing in the end. And when we replace cos alpha with 3/5 and simplify, we get s equals 9 mg over 25, which, as it happens, is exactly what they told us they wanted to find. The next thing I always do is resolve forces. When we resolve horizontally, we can find friction, at least in terms of mg. And when we resolve vertically, we can find the reaction force, again, in terms of mg. And once we've done that, well, we're in limiting equilibrium. It tells us that explicitly in the question, which means I know that friction is equal to mu r, and I can replace friction and r with what I've already calculated, simplify, and I've got mu. Incidentally, if you're confused about how the s sine alpha and the s cos alpha came about, the angle between s and the vertical is alpha. If that's helpful, draw on that extra line for yourself and mark on the additional angles when you reach that point.